What would happen if planes did not fly at 10, 11, or 12 kilometers of altitude, but at only 5,000 meters? At first glance, it seems like a minor change. They would still be far from the ground, they would still use jet engines, and the view from the window would not be that different, but changing that altitude would completely transform the way modern aviation works. Intuition misleads us. We think that the closer to the ground we are, the more control we have, and that flying at 5,000 meters must be safer, more stable, and simpler. It seems logical. Less altitude implies less risk. But aviation does not work on intuitive logic, but on physics, thermodynamics, and aerodynamics, and everything on an aircraft, from its wings to its engine software, is designed with an altitude in mind that is not accidental, the only one that makes it possible for the entire system to function. At that altitude, some 10 or 11 kilometers above the ground, the air is thinner and the atmosphere becomes stable. The engines work more efficiently, drag decreases, and the weather becomes more predictable, which allows consumption to drop to the point of making global air transport viable. Moving an aircraft weighing hundreds of tons does not happen just any old way. It needs an environment that supports it, not one that forces it to struggle at every moment. That is why proposing that planes fly at only 5,000 meters is not a trivial question. It is asking what happens when you push an aircraft outside its natural ecosystem, when you force it to fly in denser air, more turbulent and more loaded with meteorological phenomena, surrounded by obstacles with more traffic and less efficiency. From here on, the interesting part begins. If descending to 5,000 meters seems like a harmless idea, what is the first thing that starts to fail when a plane tries to fly in an environment like that? In that flight regime, the aircraft stops moving through the environment for which it was optimized, and every kilometer traveled begins to demand more energy, while the forces acting on the structure become more persistent, and the air no longer slides around the fuselage with the same ease. The general sensation is that the whole system begins to work against the environment instead of relying on it. At 10 or 12 kilometers of altitude, where planes spend most of the flight, the air is much less dense, and that is precisely what allows them to move efficiently. Friction is reduced, drag drops, and the energy needed to maintain cruising speed is much lower, so that an enormous structure can move forward without having to force its way through the atmosphere. As it descends toward 5,000 meters, the aircraft enters a very different environment with considerably denser air that changes the way each surface interacts with the airflow. That means that every centimeter of exposed surface, the wing, the fuselage, the engines, the antennas, the flaps, and the stabilizer, encounters more molecules colliding against it, and that collision translates into aerodynamic drag, the main limit to efficiency. This additional drag is not distributed uniformly and tends to concentrate first on the wing. At lower altitude, the wing produces lift more easily because the air is denser, but that advantage disappears in the face of the increase in drag. Under normal conditions, the wing is designed to function optimally in thin air, where the lift curve and the angle of attack work in balance with cruising speed, but when descending to 5,000 meters, that balance is broken. The wing needs a different angle, the flow changes, efficiency drops. The relationship between indicated speed and true speed also changes in dense air, where aerodynamic speed increases rapidly relative to actual speed over the ground. That means the aircraft must fly faster to avoid certain limits, but slower to avoid generating excessive loads. The result is a narrower operating window, where the margins are smaller and maneuvers require greater precision. All of this translates into direct consequences for the aircraft's operation, which begins to consume more fuel because it needs more thrust to maintain speed in a more hostile environment, while its range is reduced and forces it to make more stopovers, altering entire routes and exposing the structure to higher levels of vibration and dynamic loads that accelerate fatigue. All of this translates into direct consequences for the aircraft's operation, which begins to consume more fuel by requiring a greater level of thrust to sustain speed in an increasingly demanding environment, while its range is reduced and forces it to make more stopovers, altering entire routes and exposing the structure to higher levels of vibration and dynamic loads that accelerate fatigue. As the air becomes more demanding, not only does the way the aircraft moves change, but also the way thrust must be generated to sustain flight. How does a turbofan respond when it must operate outside the altitude for which it was designed? Under those conditions, the engine begins to work outside the environment for which it was optimized, with modern turbofans designed to breathe thin, cold, stable air and with a complete architecture, from the compressors and turbines to the combustion chamber and the pressure ratios designed to function in an environment that only exists at 10, 11 or 12 kilometers of altitude. At typical cruising altitude, the air is thin and allows the engine to operate under especially favorable conditions, compressing large volumes with less resistance and maintaining a stable flow throughout the entire cycle. The compressor operates within its most efficient range, the turbine remains in a balanced thermal regime, and the thrust required to sustain speed is relatively low. The result is remarkable efficiency, with contained fuel consumption, stable temperatures, and performance that can be maintained for hours without significant deviations. But at 5,000 meters, conditions change radically. Air density increases significantly, and although that seems like an advantage, it actually places the engine in a situation for which it was not designed. More air enters than necessary, not because the engine demands it, but because the environment forces it. The compressor must work harder to maintain its correct regime, which increases internal temperatures. To sustain speed, the engine needs to spin at higher revolutions, and that implies greater fuel consumption. The pressure ratio, which is key to the performance of a turbofan, is altered. In thin air, the compressor manages to increase internal pressure to optimal levels without too much effort. In dense air, that ratio becomes unbalanced. The compressor faces more aerodynamic load, and the turbine receives more flow than it needs. This causes the engine to operate hotter under greater strain and with lower thermal efficiency. The engine's work cycle loses performance. Combustion becomes less efficient. The turbine must withstand more temperature to generate the required thrust, and the compressor approaches more quickly zones of operation where the risk of instability increases. We are not talking about a dangerous situation in itself, but rather a condition that accelerates wear and reduces the service life of the most delicate components: blades, bearings, discs, seals, thermal chambers. Beyond these effects, at 5,000 meters, the atmosphere is more humid and more variable, and the engine faces a greater presence of water, particles, dirt, and ice, increasing the probability of ingestion because the aircraft no longer flies above the clouds but within them, which accelerates the erosion of the fan and the compressor and raises the risk of ice forming on the blades, with the consequent increase in vibrations, wear, and the need to activate anti-ice systems that consume even more energy. In that context, the engine was designed to perform excellently up there and not down below. Making it work under those conditions is like asking an elite athlete to compete outside their natural terrain. They can do it, but not with the same performance, nor with the same efficiency, nor with the same service life. But the change in altitude not only alters the aircraft's internal behavior, it also redefines the environment in which it must move, bringing it closer to an atmosphere that is more active, more unstable, and much less predictable than the one it encounters in cruise. What happens when, in addition to that extra strain, the aircraft stops staying out of the weather and starts flying within it? As it descends into that layer of the atmosphere, the flight no longer takes place in the relatively stable cruise environment and enters a region where the air is in constant motion, with variations, formations, and processes that interact continuously with the aircraft. Instead of staying out of the weather, the aircraft begins to move within it, exposed to a much more dynamic environment than the one it encounters at higher altitude. Most of the meteorological phenomena that represent a real risk to aviation are concentrated in the lower and middle troposphere. It is there that the densest clouds form, storms are born, vertical currents intensify, and atmospheric conditions can change in a matter of seconds. In that same environment, turbulence becomes one of the factors that most changes the flight experience, because at high altitudes it exists but is usually smoother, more predictable, and more dispersed. Whereas in these layers it becomes a much more frequent phenomenon, with ascending and descending convective currents, pockets of cold and warm air, and clouds that form and dissipate in a matter of minutes. Each of these variations directly affects the aircraft, generating more structural load, more vibration, and more work for the pilots. Among the different manifestations of this environment, storms come to occupy an especially critical place. In normal cruise, an aircraft flies above them or goes around them with wide margins. At 5,000 meters, the aircraft is within the vertical range where active cumulonimbus clouds exist. the most dangerous zone in meteorological aviation. Lightning, hail, strong convective cells, microbursts, extreme wind shear, and intense precipitation become part of everyday life. There is no way to avoid them consistently. The aircraft would have to deviate constantly, consuming more fuel, flying longer routes, and subjecting itself to greater loads. All of this turns a flight that is normally smooth and efficient into a much more complex technical experience marked by turbulence, ice, humidity, storms, atmospheric variability, greater structural loads, and an increase in operational stress. The aircraft was not designed to spend hours within this environment, it was designed to be above it. But the problem is not limited to the conditions of the air, since at that same altitude, the available space becomes much narrower when we imagine all the planes in the world sharing a much more reduced strip of sky, to the point that it simply is not enough to sustain air traffic as it exists today. Modern aviation works because there is vertical separation, with aircraft not all flying at the same altitude, but instead being distributed across flight levels that are staggered from takeoff up to 12 kilometers of altitude. Each of those levels makes it possible to separate thousands of aircraft without them interfering with one another. But at 5,000 meters, the number of available levels is reduced to a minimal fraction, so that where before there were dozens of vertical options, now only a few remain, insufficient to accommodate the global traffic that moves millions of passengers every day. Horizontal separation also becomes critical as, at high altitudes, routes remain perfectly coordinated to avoid unnecessary crossings and function like orderly aerial highways, each with its own direction, flow, and safety distance. If all aircraft descended to 5,000 meters, those routes would begin to cross constantly because the vertical space would no longer be available to stagger them, producing continuous interaction between trajectories that today remain separated and multiplying the points of conflict. In addition, at higher altitudes, traffic is completely controlled. By contrast, in that same band, one enters the space shared by helicopters, military operations, and aircraft flying at very different speeds from one another. Mixing a commercial aircraft at 800 kilometers per hour with aircraft flying at 200 or 300 kilometers per hour is an enormous challenge for traffic management, since controllers would have to coordinate separation maneuvers at all times, increasing their workload to levels that would be difficult to sustain. Added to all this is the orography, because the Earth is not flat and mountains, mountain ranges, and high plateaus limit the available corridors. Many routes that today cross mountainous regions directly would have to completely modify their paths because 5,000 meters do not offer a sufficient safety margin, forcing them to go around elevated terrain and concentrate traffic into a few natural passes where the terrain allows it. The result would be a much more rigid network, with fewer alternatives and greater dependence on narrow corridors, where any disturbance would affect multiple flights at the same time. And even if it were possible to organize traffic and sustain operations in such an environment, an even deeper limitation would appear, less visible, but impossible to avoid. The economic balance that makes flying viable would cease to exist, because flying that low not only affects safety, but also fuel consumption, infrastructure, costs, and the very model that sustains global air transport. In that context, it begins to become evident that fuel consumption becomes the first major obstacle, because aviation is sustained by a simple principle in which, when an aircraft flies higher, the air is less dense and aerodynamic. Drag decreases, allowing it to move forward more efficiently. At 10 or 12 kilometers, a balance is reached that cannot be reproduced at lower altitude, whereas when descending toward 5,000 meters, the air becomes heavier, drag increases, and the engine needs to work harder to maintain speed, triggering a cumulative effect in which the increase in thrust demands more fuel and reduces range. That increase is not minor. In certain phases of flight, it can double or even triple operating expenditure. That is when the economic model of the airlines begins to break down in an industry where profit margins are already slim and any variation in fuel cost directly affects the viability of each flight. If energy expenditure were to double or triple, profitability would disappear and fares would have to rise to levels that would be difficult to sustain, with long-distance routes going from costing hundreds to thousands, and short and medium-haul flights also becoming so expensive that they would cease to be accessible for a large part of the population. At the same time, another consequence appears that directly affects flight operations because range begins to decrease drastically. Today, a wide-body aircraft can cross entire oceans without refueling, but when operating at 5,000 meters, that capability would be reduced to the point of forcing routes that today last 10 or 12 hours to be split into several successive stopovers simply because the fuel would no longer be sufficient to cover the planned distance. Each additional stopover introduces airport fees, more travel time, greater resource consumption, and a general increase in complexity that ends up raising operating costs. Added to that increase in stopovers and operational complexity is a less visible but equally decisive effect. Structural wear also increases because keeping an aircraft in dense and turbulent air generates greater loads on the wings and fuselage, while the engines, already operating outside their optimal zone, accumulate mechanical stress more quickly and vibrations intensify. The anti-ice system would operate for longer periods and more frequently, which increases the frequency and cost of maintenance and shortens the replacement cycles of parts, bringing major inspections forward and reducing the aircraft's operational life, which would end up costing more to keep in service. From that increase in maintenance costs, a broader effect on the system begins to become visible, with airlines losing competitiveness, routes ceasing to exist, travel times becoming longer, and operating costs escalating to levels that would be difficult to sustain. Low-cost aviation would disappear completely, intercontinental aviation would collapse, and air transport would lose much of its strategic function within the global economy. The conclusion is clear. Even if we ignored the weather, turbulence, ice, air congestion, and terrain, aviation at 5,000 meters would still be unviable. It would not work from the standpoint of engineering, operations, or the economic balance that sustains the system. The industry is not optimized to fly low. It is designed to do so where the atmosphere offers greater efficiency, stability, and safety. Cruising altitude is not a whim. It is the condition that allows modern aviation to exist as we know it, because changing it destabilizes the system at every level and compromises its safety, efficiency, and economic viability. Flying that low not only reduces safety margins, it breaks the balance that makes sustained flight possible. That is why planes fly high, because only in that stable and thin band of the atmosphere do the conditions converge that allow everything to work at the same time, from safety to efficiency, range, and operational balance. Moving away from that altitude is not a simple adjustment. It is moving away from the only environment in which the system can sustain itself. And behind decisions like this, there is a universe of principles, limits, and solutions that we rarely see, but that explain why the world works the way it does. If you are interested in continuing to explore these stories and understand the invisible mechanisms that sustain such complex systems, you can subscribe to the channel and leave a like to help the algorithm recommend the content so that we can continue exploring together everything that still remains to be discovered.